Hi, friends. Welcome again to another episode of Beyond the Clouds, Edge to Edge Transformation. And this time, that transformation is going literally around the globe multiple times over. So I caught hold of this young man, Ian Curtis, and he is a very interesting guy. He's one of the rare species called PhD journalists. Ian, tell us your story. Did you always want to do journalism when you're doing cutting edge research?
Oh, hi, Shankar. Thanks for inviting me on. Great to see you again, as always. My background is kind of like bifurcated into how I got into this industry. So I actually worked out, I started my last year of high school almost 20 years ago now. So it has been a little while. But I went forward, I did a master's and a PhD in chemistry, computational chemistry at that. So one of my claim to fames is that I took the first ever CUDA course in the UK in 2009. So mathematical finance professor. I just so happened to befriend one of his students during Freshers Week. And this was, era of Facebook. I was writing, I was saying things like, "Oh, it's clear GPUs are going to be the future of compute." And I get a message from him saying, "My professor's doing a course next week on how to write code for GPUs. Do you want in?" And that kind of set my next 2.5 years of PhD and all my research papers. So I got a very strong hand in how to build parallel compute at that time. And then finished the PhD 2011 and went on a job search. And the job search was terrible. 90 applications in 6 months, lots of interviews, about a dozen second round interviews, but nobody was biting. I was looking in academia, I was looking in the chemistry industry. I even applied for a second PhD because what idiot does that? And they told me to come back when they have a faculty position. But at the same time as I was doing that, while I was doing my PhD, I was also a breed of overclocker. So the ability to tune a chip to get higher frequencies by pushing higher voltage, managing the thermals, and then using exotic cooling, like liquid cooling or sub-zero cooling, solid carbon dioxide, liquid nitrogen. Didn't participate in any liquid helium events because that's a little bit more expensive. But turns out liquid nitrogen is about the same price as milk. So it's actually quite affordable. But all through tuning systems, I was writing guides on how to get the best out of your hardware from the hardware that I had. Through that, I met a journalist and editor at a website called Anantech, which was a website that was built, by engineers for engineers. It was that website would review the latest in consumer and enterprise PC hardware, but write it in a very engineering focused way, looking at microarchitecture, looking at why does the iPhone 4 lose signal when you hold it the wrong way. The website Anantech was one of the first to actually quantify that in terms of volume. And I was there for so while I was writing for them, became senior editor. When the PhD route didn't work out, I said, let's go full-time freelance on this reviewing hardware thing. And then 5 years later, salary position, stayed another 6-7 years after that through a couple of acquisitions, ended up being part of a big worldwide publisher. And then decided enough's enough being a journalist, even though I was doing 150, 200,000 miles a year, lots of events, CES, Computex, Mobile World Congress, and then a few personal ones like Hot Chips. I decided, and through peer recommendations, to become an analyst. One of these tech analysts that help companies translate technical information into something more broadly digestible. Through either message testing, strategy discussions, or in my case, it's a little somewhat unique, is I do a lot of content creation. So in about 2020, I started up a YouTube channel. I called it Tech Potato, which has a funny story in itself. That's AI generated from Google's own caption engine with a live stream I did with another content creator. That kind of determines the name for that channel. And I've kind of retroactively advertised it as I talk about twice the tech and there's some chips, Tech Potato. That I call my analyst firm More Than More because I needed something a bit more presentable if I ever go on TV. And it turns out Pat Gelsinger likes the name. It's the Gordon Moore company, right? So the CEO of Intel likes the name. And yeah, people ask me, don't you ever use what you studied in your day-to-day job? The minute I moved from a freelance to a full-time journalist, instead of doing PC hardware, I was doing more looking at either business or hardcore semiconductor research, and going to IEEE events, being able to sit in those tutorials, being able to digest information about work function metals and the future of transistors and backside power delivery. Before it was called backside power delivery. I remember seeing it in an ARM presentation like 2016 as, the very early vestiges of dealing with something like that. That's where it's been really helpful. But yeah, I did my 10 years in the mines as a journalist, and I came out, and I'm now this analyst influencer thing. The YouTube channel just hit 110,000 subscribers, which is really fun. But through that, I've got clients and work with clients going through complex topics such as quantum computing and the roadmaps into quantum computing, deep dives into things like Tesla's Dojo AI supercomputer. I run a semi-irregular TV show called the AI Hardware Show. That's between me and Sally Ward Foxton of EE Times, where we just season is 12 episodes, and each episode we go through 6 pieces of AI hardware, what they're about in the market, whether it's silicon, whether it's IP, how well funded they are, how well supported they are, software, what the customers are, what the potential is, and we do a podcast with that as well. And that's been really well received. We're actually just starting to plan for the 2024 season. And I keep asking AI companies, when's your big announcement in 2024, so we can plan when to start recording it, because we want to start in Q1. And they're like, no, wait until Q2. We're going to have some stuff by Q2. And I keep saying, we'll get to it quickly so we can start recording and start planning. But yeah, it's ever since transitioning into this sort of analyst role, I formed my own company. I'm now my own boss. I get to focus on what I love, and what I love is that fundamental research into silicon, new silicon architectures, finding business use cases. And I've done, so we're at the end of 2023 now, about a dozen or so presentations at various conferences and events. I keynoted one of IBM's developer events, and I was recently at Lattice developer conference at a panel speaking about AI hardware and some of the fundamental aspects of the semiconductor industry. So I find it fascinating. I could speak for hours, not just about me, but about the industry too.
That's what keeps you young. You're so full of energy, probably morning to evening. Who would have thunk that you graduated more than 20 years ago? But seriously, I love what you're doing, which is initially geek to geek journalism, geek to geek marketing, and now geek to geek analysis, really bringing the best of what's happening to the people who need to do either financial analysis, technical analysis, decision making. How did you even think about it? I mean, other than the fact that you accidentally met some journalists, how did you think that there is this big need? It is really
Well,
getting complex today.
it's when you're in research, you learn to say what you're doing in a very technical way. These are the experiments I'm doing. This is the code I'm writing. This is what I'm going after. When I was in that overclocking mode, writing guides, that felt very much the same. And then you realize that not everybody can follow a guide. Not everybody can follow step by step. Because we have it with mainstream media today. It's more storytelling. You have to be able to tell that story. You have to be able to introduce complex topics, at various levels, depending on who you're talking to. I mean, if you go online to YouTube today and look at Wired, that they do this series where it's like explain concepts at 5 different levels, starting with a child and ending with an expert. And they do things like quantum computing, astrophysics. That's how to explain relativity at 5 stages between a child and such an expert. And you realize that there's such a high demand for that, and being able to tell that story is a skill in of itself. We always talk about STEM, science, technology, engineering, mathematics. There's a small group of people, and I think I'd consider myself one of those, that are not saying STEM anymore. We're saying STEAM. And the A there is for arts, the ability to be creative. And it turns out engineers are some of the most creative people on the planet. They just do it in a very technical way. I mean, I was just saying to you before we started, a story of a guy working on his 7th generation memory controller, right? He'd been at the company, 10, 15 years. He didn't know what the memory controller was going on into, what products it was in, but he was just so invested in that memory controller. And if you wanted to ask him about it, he would bite your ear off as a chance to tell you, but he never had the emphasis to actually work out what was going on around it. So a lot of what I do these days is also help with internal communications. One of the best compliments I got, and just to toot my own horn again, the chief architect for one of the big mainframe processors, he reached out to me and said, I showed your video of my product to my wife, and after 5 years, she finally understands what I've been working on.
Oh,
Right.
perfect, perfect.
So the ability to tell a story is vital for engineers, and most of them is just so creative anyway. They just haven't had any practice or confidence, and there are things you pick up along the way if you actually go out and do that. I mean, in my youth, I'd be playing. I'm tone deaf, but every so often I like to create music or something that sounds nice to me, and the fact that I was writing guides for overclocking just naturally came out of the love of what I was doing. So it has to be the future. We always talk about the melding of hardware and software to find the right products for a company to promote, and companies are always wondering, how should we promote something? What's the right way to talk about it? How do we talk about it to the masses? Should we get the chief engineer up on stage talking about it, or should we get a junior engineer? Well, if you can have those people who know how to create a story around what they're doing, be able to provide context, then you get a company who knows who they're talking to, and B, can talk to them. And sometimes that's quite rare. I don't expect it from startups day one, but you can tell the startups that actually hire storytellers, because they're the ones that are getting the press coverage. They're the ones that are reaching out. And they're the ones that talk to me the most, and the ones that I end up enjoying speaking to more, because one storyteller to another is amazing, at least in my opinion.
Very true, very true. What you're doing is a lot more than more, explaining more to the people out there so that they understand what's going on. And interestingly, I started my career with the DRAM controller on the Pentium. Then later a cache currency controller, but I couldn't sit in my cubicle. I always wanted to go see what others are doing, ended up in marketing. So one thing I've always believed, and you brought that up, is that scientists are not just doing science, because it's not like A follows from B follows from C. If it was that simple, robots could be doing science, right? So discovering in science is really an art. And then you have to go beyond the art and science into practices. In other words, you have to make real products. What's your thought on that? Because I see you doing all of this. You're not just doing science, you need to understand it. And there's that art part of it, which is understand and explain and almost synthesize what's going on. And then you're putting it into practice. Otherwise, people won't give you credit for really understanding what's going on.
It's funny, because I will sometimes look at some research or some development that will be completely out of left field, completely orthogonal to traditional thinking. I'm like, that kind of works. What was that person smoking that day to think of that idea that actually become a massive research project? Creativity is important, and it's always in the place where you least expect. One of the things that I like to say is the people who make the tools don't always know what the tools will be used for, right? You can't predict everything your customers are going to use it. Look at graphics cards now with machine learning. Nobody knew they'd be used for machine learning. Obviously, or the Henry Ford quote, if you ask what the consumer wants, they only want faster horses, not cars. So it comes from both sides, right? It's quoting both sides of the fence here. From my perspective, it's a case of who do you want to talk to, and the problem is a company doesn't always define that well. this is why in marketing and media we have this concept of B2B and B2C. But communications is like that. You're either doing your communicating business to business, or you're doing your communicating business to customer. And you expect business to be somewhat literate in the product space, because otherwise you wouldn't be speaking to them. Whereas with customer, you might all have to bring everything up from first principles again and again and again. Turns out if you do that 100 times, learn how to do it well, especially if you're able to get feedback and work under a mentor who's been doing it 100 times as well. So there's always a demand for that. I also deal with people who are so amazing at that, they forget to highlight what's important. So even if you do put out tons and tons of information, all of it amazing, all of it really good, if you do too much, it's white noise. And you have to have the curation of what's important, because not everybody has the time to sit through and do that. So the ability to it's almost finding the story, but as a second order deviation, right? The first order is all the stories you've made, and the second is, well, what stories out of those are the most important? And ultimately, it's that second stage is like the research you might see in Nature. I think publications like National Geographic and that do this really well. They're able to pinpoint out stuff that's really important of second order out of the research and build a story around it. And what do? They hire experts to help tell the story. And it's the journalists who reach out to experts to get an understanding to help tell that story that you actually see get pushed through and become better and better and gain bigger followings. On that side, I always tell people, don't follow a publication, follow a journalist, or follow the writer, because usually it's the writer that has the morals and the research nous and the ability. And it's always funny in our industry as well, because sometimes you'll get them that are traditionally classically trained as journalists learning about technology, or there'll be engineers learning how to write. And I think we need a lot more people to come and be that mix.
Very true. What I find interesting is that it's very rare that you'll find a musician. On one side, they do rap music, and the other side, they're doing classical, or a cricket player also doing soccer. And that's what I find very interesting about your work. You've got Tech Potato, which I'm sure is a very different market, very different vibe to it. I've seen it. And then the much more serious, more than more. How do you balance it out? Number one. Number two, do they feed into each other, or are they completely separate? How has it helped you to be who you are today?
So so even though Tech Potato came first, More than More is the overall company, and Tech Potato actually sits as a brand beneath it. And the way I characterize it is More Than More is the business side. So it's more the internal consultancy with a bit more of professional outreach, whereas Tech Potato is the external communications that's more social media focused. Part of being for as much as we love or hate the word influencer, so some people say science communicator, but on social media, that sort of thing. So the way I've separated it is this sort of internal and external way of thinking. That helps because I will have clients and engagements where they'll only deal with one side or the other. It's very clear that they actually want to have phone calls and discussions versus they want help promoting their message. And as you know, we have so many different companies with so many different philosophical styles out there. Some of them are very rigid and reserved. Others are a bit more, let's play the social media, the viral game to get some of the message out there. And having these two brands essentially helps with whether I'm dealing with company A or company B. Though that being said, I did a project with a company that I thought would be very reserved, but they actually wanted it, full meme, full social, viral, everything in it. And that was quite fun. that was the first project I extensively used machine learning in. So okay, story time. They had a new product for semiconductor manufacturing in the fab, and I wrote a script, a 10-minute video script, so about 1,200 words or give or take, talking about their new piece of hardware, why it was important, the technical aspects of it, but also what it means in the grand scope of the future of semiconductor production. I wrote the script, I put it into a large language model, and I said, make this more accessible. Make it so my grandmother would understand it, essentially. It took a few tries, a few iterations. I got lots out. I then pieced together a version that worked, and it came back, and basically it changed the story from what I'd written into, it created an analogy of the equipment being like a chef in the kitchen. So you could be a master baker, a chocolatier, a sous chef, a saucier all at once, and change it on the fly. And I went to my client and I said, here are 2 scripts. Which one would you like me to do? They chose the one that was enhanced by machine learning. And in that video, it turns out while I was aiming for 10 minutes, it was actually around 7.5 after editing. And I thought this needs a little bit extra. So I used another machine learning tool trained on my voice to do 40 seconds of voiceover. And I added some B-roll into the video to make it a little bit longer, explaining one of the other aspects of the product we wanted to talk about. But it was an AI trained on my voice, giving my voice back based on what I'd put in as words, and nobody could tell the difference between me actually speaking into the microphone and the machine learning model. 6 months ago they could, because I tried it before back then, but this was a proper full 40 seconds. Nobody said anything. I think that video is something like 60,000 views now. So
wow, so you cloned yourself essentially to create different. You could even create an orchestra at this point, right?
Well, there are some fun things going on with audio right now. We are still touching the surface on what's possible that side.
What I find interesting is that even early on, you pivoted even in your PhD program. I remember those are the days I used to work on one of the first 3D graphics chip at S3 before NVIDIA became the #1 company in 3D graphics. But at that time, it was primarily for fun stuff, GPUs were used for graphics. And NVIDIA kept imploring that it can be used for serious stuff. How was the transition like from computational chemistry to using GPUs and then doing a whole bunch of other things like?
So prior to my PhD, a little bit in my undergraduate, I'd done some basic coding, C, C++, what have you. This was back in it was probably Pentium 4 days, and everything was still very single-threaded, right? And because I was doing chemistry at the time, I was looking at what was going on, and it was very clear that computational chemistry had the angle to, can you test to see if 2 molecules will combine together given conditions? If you can predict what will happen, you can then reduce the search space of how many chemicals you need to test down by several orders of magnitude, because you could do it all in compute, and then it just becomes a scale-out problem rather than a chemistry problem, essentially. And so that was my thinking along that route. And then we were slowly getting into this sort of multi-threaded era, with Pentium D, and then we started to see, Sandy Bridge and Ivy Bridge start to come out. That was, and then like Phenom 2X6 from AMD, and then Bulldozer. And while I wasn't necessarily hooked into proper HPC at the time, it was very clear that this was going to be an algorithm problem followed by a scale-out problem. And then, of course, GPUs come about, and it turns out that if you have a bunch of vectors, it's very, then as long as you can map your compute, then it should work. Problem is the tools. And so me just randomly espousing that computational chemistry has a massive future in predicting outcomes of future reactions came into be learn about this new hardware. I mean, that was 6 months into my PhD, but in those first 6 months, what I'd done in the research group I was in, the research group I was in was not computer scientists. I'm not a computer scientist. It was chemists learning to write code, self-learning to write code. So it was all pretty bad. It was all serial. One of the first things I did is apply OpenMP. Let's go parallel with some of this code, because a lot of it was, looping over tri-diagonal matrices, and that you can parallelize fairly straightforwardly. So we're doing that on literally going from single core to quad core. And it made the simulations faster. Then people complained that they could only run one at once rather than four at once. So we had to get over that. And then the fact that this CUDA thing came around, and the ability to learn how to program a GPU, back at that time, there was not much documentation on how to do it. The difference between a high-level language like CUDA and a low-level language like PTX, and trying to optimize out of code. Oh, I went on the course. I actually went on the course the second year it was done as well, just to make sure I didn't miss anything. And the online documentation wasn't fully there either. But it turns out getting a 2000 speed up over single threaded code was possible using a GPU, and you're like, dang, this is definitely going to be what we have to use going forward, as long as your algorithm can map to it. I think in one of my research papers, I ended up showing there's in my field, there's like a godfather of computational electrochemistry, who wrote a book and basically said, this method is impossible because you'd never have enough computational time in the universe in order to be able to do it. And I disproved him by using GPUs 30 years later. But and then going from that, looking at some of the stuff he'd done, being able to show speed ups of 80,000 or 100,000x in some of these codes, what he said would take a month ended up taking me 20 seconds on a 2009 2010 GPU. And then it just really clicks that, yeah, we got to get in on this. And Nvidia did in a big way, obviously. That's why they're a $1.2 trillion company now.
Very true, very true. I remember learning all about neural networks, and it was a great idea in the 90s. And again, multi-core machines, massively parallel architectures. None of that could happen because we didn't have the compute power. But today, it's all possible. But you touched upon something very important. It wasn't just hardware. There had to be a confluence of hardware, software, platforms. Could you, for the sake of our audience, simplify and tell what did it take to go from those von Neumann serial computational engines, where the gods of chemistry would say it could take months to do basic things, say sequencing the genome, to what we have today, which is doing things in parallel, collecting information in parallel, machine learning? What did it take?
Well, annoyingly, there's there's several barriers to this that don't know each other, which is annoying. You've got the hardware manufacturers who are building the hardware. They don't know what people want. They don't know, talking back in the day, they only know what people want through people that they sponsor. So in the case of where I was, they were sponsoring this professor in mathematical finance. So they were focused on how do we improve hardware for mathematical finance? How do we improve software for mathematical finance? The other side of it is all these fields of research didn't know that this hardware existed to be able to accelerate it, because as you know, academics tend to be in their own little bubble, only knowing what's going in. So what had to happen essentially was cross-domain knowledge transfer, going both ways, from the research to the hardware manufacturers, to say we need a set of libraries to do this. Now, in traditional compute, speaking all the way back in Fortran days, and you've got things like Numerical Algorithms Group, NAG, and Intel's obviously had ICC for ages. This is well known in very specific circles. You start to expand it out, especially at that time in the late 2000s, early 2010s. You ended up creating a tool that a lot of people need, but not a lot of people exist. and it's literally through word of mouth. I don't think my studies would have been the same if I hadn't have made a random comment on Facebook and this guy I'd befriended hadn't seen it and invited me to his professor's discussion point. Because again, nobody knew what the documentation needed to be, let alone the library support. And that has thankfully evolved to a point where now communication is actively going both ways because people are going out and looking. This week, as we're recording this, I recently did a talk at a university, medical AI, right? So they're doing machine learning for medical use cases. And they invited me to give a talk as a non-academic, one of the very rare non-academics they had presenting in their colloquia, to basically talk about the hardware industry. And I went in, I started talking about, like transistors, Moore's law, then digital compute, and then some of this, von Neumann compute, analog, optical, then going into what the AI hardware industry looks like, big players, small players, startups, all the different types, and where these companies are starting to get pinpoint exact niches for themselves. I did get a fair number of glaze over eyes, because me being in this industry for so long where I am, I think about it from a very business-like context. Whereas they're mostly using either x86 CPUs or NVIDIA, because it's AMD, Intel, and NVIDIA who are going out speaking to universities. And because they're practical research rather than fundamental research, they're taking what the fundamental researchers have kind of provided to the hardware players. So I did get a number of questions about, is there going to be anything more than CUDA, machine learning frameworks like PyTorch, TensorFlow, Onyx, and the future of those. But also why NVIDIA has such a big lead in machine learning versus what are all these other companies going to end up doing? How are they getting a foot in the market? So things like having unique things like batch one latency, having chips as big as your head, like the Cerebrus wafer scale, and doing unique things in terms of scale out that traditional GPUs haven't been doing. And companies like AMD are getting there, but NVIDIA still hasn't bifurcated its strategy yet properly. But that's an interesting thing in the fact that, going back to the software argument, NVIDIA and AMD have roughly the same amount of employees, and they say most of their employees are software engineers because they have to be these days. But NVIDIA only has a few product lines that their software engineers can optimize on. You buy that $100 NVIDIA product, your code will work on a $40,000 NVIDIA product. AMD has so many different product lines that are, non-compatible with each other in terms of code. They have to split their coding out. So people say, well, AMD doesn't have the same software support. However, they know where they need to be. They just need time and people. And so they still, even though we've gone through, peaks and troughs in the last few years about chip demand and chip glut, the demand for software engineers is still as strong as ever, because without software, the hardware is useless.
True. And you brought up many different points. One is the silos. In the academia, it's extremely siloed even today. There's hardware and software, and within hardware, there's, those who make CPUs, those who make GPUs, those who think about memories and all that. But aren't these silos killing us today? The problem seems to be we don't need, just like what Henry Ford said, we don't need faster horses. Do we really need faster CPUs? Do we need faster GPUs? Or do we need computational engines that can help us solve our problems, which could be a mix of these kinds of technologies? What's happening, in your opinion? Are we doing the right thing by just speeding up different types of processors?
It's a multi-pronged attack, right? There will always be people who want the one thing as fast as it can go. They'll always need the one that you always need. Like the finance industry loves very fast CPUs because they're the ones with the out of the lot is the lowest latency for the pipeline usually, unless they have a dedicated ASIC. Then you've got the gamers. All they want is faster GPUs. How many frames per second? We're now going from 1080p to 4K to 8K, 60 hertz, 120 hertz, 240 hertz. I even think there's 500 hertz monitors coming soon. So, game designers are just building so much into their games now. They want them to be photorealistic. So you need the compute power to do that. However, we're now getting to a point where we have modern workloads today that can take advantage of multiple different forms of architecture. So we're starting to see them all come together on individual products, not just systems, but products. That's why we have NVIDIA with their Grace Hopper, ARM CPUs paired with a Hopper GPU. So I was seeing AMD's just announced the MI300A CPUs paired with GPU paired with HBM. Sorry, excuse me. And the open chiplet marketplace, this idea that future process nodes are incredibly expensive to build on. So let's move it into smaller chips optimized for processes and then bring them together using high-speed interconnect, which we've developed over the last 10 years to make that an actual possibility. So even though there are, if you think about it, like a three-dimensional model, CPU, GPU, ASIC, the pure axes, the pure performance are still going guns. It's just how do we fill in the middle? And that while there are silos, there's enough speak about how do we combine them in the right way. The only thing that's going to stop that is money, because making these things and building for them is expensive, and people making this hardware, especially on the bleeding edge, have to have the business use case for it. I always speak to companies who are trying to compete with NVIDIA. It's like, if you build a product that performs, as well as NVIDIA, you're going to have to be priced the same as NVIDIA to be competitive, or a factor 10 less, right? But then you have to sell an order of magnitude more, to meet your revenue targets, to meet your venture capital funding. It's for the AI startups. For all that I follow, aside from a few of the ones that play in the edge, out of the big chip unicorns, only one has more revenue than funding that they've raised, right? And there's like 10-15 billion dollars in that industry right now in just hardware. So the fact that only one is winning right now, or one has found a niche that is actually paying, is setting off some alarm bells somewhere. However, I recently published my list of total funding to date for all the AI companies I track. Between last year and this year, I only removed one company from that list. And that's only because I haven't heard from them in 4 years. So I kind of assume they're dead. They haven't announced how much funding. They haven't raised any new funding in that time either. So these companies are still about. They're not dying. So this whole thing about how do we fill in the rest of the graph rather than the pure axes, we're in a moment where it's so fast paced and it's so hard to describe as well. It's so hard to translate. I was actually recently at the BBC, funnily enough, because that's a short distance away from me. They're building a series on AI, and they wanted some advice on how do we approach the topic of AI hardware. And it's funny because they're TV production researchers, right? They're not engineers. They're not domain experts, because they were doing AI this quarter. The next quarter, they might be doing something like Planet Earth, which is, something else. So I had to go forward and talk about training versus inference, hardware versus software, major players versus startups, fundamental research versus end use points. And then halfway through the question, they'll be like, well, where does quantum computing fit in? And then you realize you got another hour. Take me another hour to go through that as well. So there's clearly a lot of, if the broad media are looking for ways to communicate all of this, regardless of whether it's siloed axes, points, CPU, GPU, or this sort of heterogeneous mix of compute and memory, or programmable compute and that sort of stuff. There's a lot going on right now, and I'd match some of my peers in the industry in saying we're in a golden era. Right? When was the last time you saw so many hardware startups get so much funding to start playing with some of these ideas, to be able to look into the research for all these things? The rise of RISC-V as well in a lot of this stuff. It's if you're going to be in semiconductors, if you're going to be in chip production, if you're going to be in software design, this is the decade to do it.
Very true, very true. I started off on the Pentium, and so much has changed since then. You brought up some very interesting points, which is for startups, and there are almost like 100 of them in AI, from inference engines to machine learning and the big iron supercomputers to single wafer chips and all that. It's hard to conceive that they will be able to compete effectively with the incumbents because there's so much more at stake. They have to either be different in terms of technology, significantly different, and or much cheaper. What do you think? Do you think the incumbents will continue as is, or will there be a few new players who would change the game?
A couple of those new players are my clients, so I have to pick my words very carefully here. The ones that I find that are seeing light at the end of the tunnel are more than simply one-trick ponies. What we're seeing right now, especially with machine learning, is that the two main markets that need that hardware are machine learning and high-performance compute, which are kind of two sides of the same coin. And it's the chips that can do both and not just machine learning that are seeing more use cases, or they're able to show off more research papers, more test cases, more being able to say that you're in like these 5 major Fortune 500 companies and these 5 major universities doing hardcore research. Being able to show that you can have customers across the whole spectrum, that's where a lot of at least the big chips are winning. Edge is a very different use case. But even for the inference in the cloud chips, finding chips that also work for low power compute and scale out and then having the programmability in there is becoming more and more important. I mean, say earlier, one of the biggest questions I get is who will dethrone NVIDIA? Right? Not just in training, but just in general, because CUDA's had 15 years to bubble up through universities. And if you look at purely from that perspective, you'd say, well, nobody can compete with that. The only way NVIDIA would lose is if they cripple themselves by having a bad product cycle. The one thing that is leveling the playing field are these programmable frameworks. So rather than targeting CUDA or targeting PTX or using ROCm or OpenCL or SYCL or SPIRV or whatever, you target PyTorch, you target TensorFlow, you target Onyx, and then you use the relative compiler for the tool you need. Now, of course, if you've got generic code and you're using a bunch of compilers, it's not going to be optimized for each piece of hardware. And what we're seeing right now is in the use cases for this hardware, a bifurcation. Support for those high-level languages means that you can almost write code once and it will run anywhere. That's kind of the goal, like one API as well from Intel. However, a lot of the companies that are actually saying, well, we're putting $1 billion of hardware into this, if they can optimize by 10% by using the lower level language, then they will. And that's where CUDA, that's where PTX is coming in. And so we're seeing some of these startups realize that they have to have high level and low level languages in order to compete. Because when there's a business use case, there's usually a way. Whether that's hiring expensive engineers, because right now, if you want a GPU from NVIDIA, there's a 52-week lead time, right? So if you can hire some engineers in the meantime to optimize for some other piece of hardware, then maybe that's your cost benefit analysis over the next 3-5 years sorted. And it's so weird how the market dynamics are today with the demand for hardware, with this limited amount of packaging from TSMC and all these players coming in, there is more chance than not than there will be disruption despite having massive incumbents. If you could order an NVIDIA system today and it would arrive tomorrow, I don't think there would be that same level of competition.
That's true. So the market demand itself could be its own enemy in the sense that not being able to satisfy the market can change the whole dynamics.
The funny thing there is the hyperscalers might do some of this. People like Microsoft, people like Google, people like that are building their own chips. So they're buying less from NVIDIA, which means there's more NVIDIA for everyone else.
Mm-hmm.
So that's just a potential wrench thrown into the mix that actually people say, well, it means that startups can't sell to those big hyperscalers. So that's a negative. But then if it means there's more GPUs for everybody else, that's also a negative. So yeah, there's so many things going on macroeconomically as well.
And if you really think about it, once the hyperscalers can prove their business case internally, like an AWS or a Microsoft Azure, there's nothing really that stops them from selling them commercially if that's a lucrative market. Because look at the price points today, it's insane.
Well, so this has always been the argument for ARM in the cloud, right? So even though Amazon and Graviton they're using Graviton extensively internally, and they have Trainium and Inferentia, their machine learning chips. However, on cloud, x86 is still their main customer base because that's what people are familiar with. So you'll always have an incumbency, and some people have switched over to ARM. But take Google with their TPU, they only want to use it internally. There's very limited external use, because they see that as their market advantage. They still have GCP, Google Cloud Platform, which is mostly x86 and ARM, but not their own chip. So
very interesting.
It's let's not get started on the Chinese cloud market either, because that's an entirely different thing altogether.
Yeah. I mean, one of the things I find interesting is that the Hot Chips conference, now it's become an oxymoron. I mean, who wants hot chips, right? We need cool chips. What is your take on that?
Cool Chips is another conference that's usually a few weeks earlier.
Exactly.
But
it's no longer just performance, isn't it? The PPA and the.
Everybody's been talking about efficiency for ages as well. It's this boom and bust cycle of performance, efficiency, performance, and the point is, how many times can we do that cycle before we actually run out of physics? We've had Intel and a couple of other companies start talking about 1 kilowatt processors. 15 years ago, we were talking about 100-watt processors. So the fact that we're going, an order of magnitude in 15 years I don't think that will happen again in the next 15, by the way. But TSMC has published research and they can, with the right manufacturing tools, cool 2.6 kilowatts with chilled water at a low pump rate. So that could even be improved. There's something to be, because some of these workloads are just massive scale out problems. We hit on Amdahl's law so early on, the ability to scale your serial versus your parallel elements. And if you're limited by your serial, it doesn't matter how much you parallelize, you're never going to get that speed up unless you make individual chips faster. So you only need to scale out less. So even though some of these things are now approaching a kilowatt, they're still being built for efficiency in mind, because all of the little cores are still at the more optimal voltage range than that's what they're designed for. The flip side, we're seeing things like cryo CMOS come out, so the ability to actually run hardware in liquid nitrogen environments. And it turns out if you're designing silicon for that, that's a totally different way of thinking about it. It's the one thing I will say about Hot Chips this year, though. Hot Chips is a great conference. I go in person every year I can. I have done for almost 10 years now. And it's when we were stuck in the pandemic, I do like watch along parties on YouTube for the people that were going. And the one thing that changed my perspective this year is that it wasn't just an engineering conference. there were investors there. And I mean, not just one or two, at least a dozen. Because investors are now seeing the point where, well, we need to know what companies we want to invest in that might have a potential of disrupting the future. How do we do that? We go to deep engineering-based conferences and IEEE conferences to find out what's the next big thing on the horizon. So we're not only planning 1 to 2 years out, we're planning 5 to 7 years out now. And for me, that was kind of like a mind-breaking shift, being at the event. And I come away with 3 more meetings to speak with investment funds because they want to know about, this company or that company. It's like, oh, I saw this one present for the first time and I didn't really know who they were. Can you dissect them for me? And it's a company I've been following for a couple of years, so of course I can tell them details for a price. But yeah, it's that there's a fundamental change. It raw chip design and production and retail just isn't a thing anymore. Everybody wants to be involved at every level. The reason why car companies are hiring tech CEOs now is because they need to be part of the chip chain. You've got 1,000 chips in a car or more. You need somebody who knows that industry, because if one of them gets limited, how do you roll them off the production line? And we during the high levels of chip demand, we saw that, and that's why was it the head of Infineon went to Ferrari's new CEO was ex ST Micro or something. That's one of it's that sort of thing. It's like, wait, what? He's now head of a vehicle company? What? Oh, and then you realize it's demand for tech CEOs rather than car CEOs.
Is the cell economy. In fact, it's interesting. When I drive, I succumbed to it and started driving a Tesla. And it feels like an iPhone on wheels, literally. I mean, it's not really, the good old mechanical driving. But I'm like, okay, I have to be careful, because if an iPhone wants to reboot, it's okay. I don't want my car to reboot on the way,
Well,
what's your take on
this is why regulation is becoming so important, right? That's why you have real-time operating systems, and you need fail safes, and that's why you have ASIL B and ASIL D and ISO 26262 and all these different standards for things that actually matter. I mean, you drop an iPhone and your screen breaks. If you have a little bump in your Tesla, you don't want the whole thing to shatter, right? So it's the thing is, people are always worried about new technology. So the technology may be well ahead of where the regulation is. I've had a chance to be in like level 2 self-driving and level 4 self-driving. The level 4 was with Mobileye in Israel. We did a 10-mile pre-programmed loop. It had cameras, it had LiDAR, the brains were in the back. Now, obviously, this was a dev kit, not a full system for retail. So it was using a lot more power than it should. It wasn't optimized silicon. But the algorithms did that 10-mile loop with no interventions, some of it on like unmarked roads. At one point, we had cyclists jump in, and it handled it fine with 0 interventions. I'm like, this for point-to-point commute for like work and stuff, or robo taxis or whatever, this is ready. What's not ready is government regulation and people support. That's the thing. You can't have electric vehicles, for example, be as good as humans. You have to have it an order of magnitude better than humans. But even then, people will say 1 death is too many. You can't trust a computer. That might be a generational thing, right? It may, the generation beyond us, or 2 generations beyond us. I always joke that we always went, Gen X, Gen Y, millennials, then Gen Z, then Gen Alpha. Really, we should be calling it Gen AI, because that is the generation that's going to have artificial intelligence, machine learning, and generative AI as part of the tool set growing up, right? I'm lucky to be of the generation that essentially went through high school pre-smartphone. We still had dumb phones and we still played Snake on our old Nokias. But now we're in that generation of, those who grew up with smartphones during high school And now we're in a generation of, well, these are kids that are going to have machine learning, but direct interaction with machine learning through high school. Speaking to a person the other day, and they're saying that as part of their university courses now, they're having machine learning classes, but how to use it in an ethical way. What are the limitations of doing it? And that's only going to come down as we get to the younger and younger students. And regulation will evolve as people's attitudes change, as people are more comfortable with it from an earlier age.
I recently interviewed a good old friend, Rebecca Wheatley, and she's
Yes.
creating nursery rhymes using GenAI. And,
Yes.
stories for her kids. They want cat stories. So using GenAI. And that I thought that was super creative because what's the worst thing? A hallucination can create a new story and it doesn't have to be perfect. It could be something fictitious, right?
So the devil's advocate there is, for people with children telling stories to their kids at bedtime, you had to have some amount of storytelling ability to do it off the cuff, to generate it. If you no longer need to do that now, maybe we'll lose that skill. But maybe that's just part of the human evolution with technology, right? So every technology has its detractors. And the part of ethics in AI is as deep as it is wide as well, with every nation doing its own little thing. And yeah, it's I was speaking to, again, some of the medical AI students at the university, and they're saying how they went to go generate an image of people using one of these Stable Diffusion, Midjourney, DALL-E type environments. Even though they put in a prompt, the system they used added words like, gender, balanced, diverse, to ensure that the model output was fair and balanced. So not even talking about the input data, but also managing the output data. So, and for things like that aren't generative, like Amazon purchases, social media feeds, nobody knows what's going on behind the curtains there, apart from the people who work. And to do regulations on that as well, technology is moving so fast, and yet governments move so slow.
And it's hard, right? I mean, to a certain extent, we are talking about regulating human behavior. So we are putting human behavior on steroids, and there are biases in society, whether it's gender balance or it's ethics or whatever. And we're just making it on steroids. So the question is, at what point can regulation help? It's a tricky one, isn't it? So let me ask you the mandatory questions.
Go on.
Quantum computing, neuromorphic computing. How real are these? I mean, how long do you think it'll take for a real quantum computer to become commercially viable, or neuromorphic? Because again, the understanding of the brain is changing all the time. What I studied 20 years ago is very different from what's happening today. As we get better technology, we can see from fMRIs that maybe the way we understood the brain 30 years ago is completely outdated compared to what's happening in the brain today. So what do you think is happening in these areas?
So quantum computing is already financially viable, though only for companies selling quantum computing in the cloud, not actually companies selling them themselves. That being said, IBM just had their AI summit, their yearly AI summit. And I wrote a post on my written blog that's more-more.com about their summit. And their big thing is having a reliable roadmap, not simply just to commercialization, but just advancing the science going through. So everybody talks about qubits and logical qubits versus physical qubits, and error correction, error mitigation. And you'll often hear things like, oh, well, a quantum computer has to have 1 billion qubits because of errors in order to get something real. And so what companies like IBM are doing are they're saying, well, there are these like 8 orthogonal things that can be worked on independently, different abstraction layers, and we could optimize every single one over time to be better. That helps the overall product. So right now they're looking, their recent papers in Nature outperforming classical computing for some physics simulation. There was 100 qubits for about 4,000, 3,000 gates. And gates in this instance is how long can you take the data and use it concurrently for more algorithms. Their roadmap shows that in 2029, they expect to have 20,000 qubits, but 100 million gates. So going from 3,000 gates to 100 million is such a massive jump. It means you can actually do long-term math on it and still get reliable results out of it through error correction, error mitigation. And quantum qubits are always spoken about in terms of coherency time. How long until the qubit collapses, right? And right now, the best qubits can do like 200-300 microseconds. In order for IBM to hit their target, they need to have that time up to 1 second, which sounds insane today, but they've actually detailed it every year by year, what they're doing to improve on that roadmap and the technologies they need to invent with a yearly cadence in order to get there. And they're fairly open about that in terms of the high level, these sorts of couplers, this sort of software management. This is how you optimize code. I mean, take for example standard x86 code. You've heard of this concept of optimizers and super optimizers being able to reduce the code for memory, footprint, and compute capability. They're already doing that in quantum computers to reduce the number of gates, to reduce the number of qubits they need to use for a mathematical operation. We have quantum Fourier transforms today being run on quantum computers. The head of IBM's quantum computing division posted on LinkedIn that since they've made their systems available in the cloud, 3 trillion circuits have been run on quantum computers, and there's like a couple of billion more every day being run. If you want to rent time on a quantum computer, it's like $2 a second, just for context. So it's not like a couple of, it's not like $20 an hour for GPUs. It's actually a step above. But the problem that quantum computing has is that we have a couple of companies that are proper full stack pushing that forward. But then we have 50 other companies who are looking at fundamental research and just doing 1 or 2 things in that stack. And unfortunately, it's those companies that are getting most of the column inches in the media because they have venture capital funding to go and be bold and creative, because they have to be in order to find out where their potential clients are going to be. So for quantum computing, it's still a 10-year technology to commercialization, but people are making money on it today. And very smart people have thought about that roadmap and where it needs to go and how it's going to get there. So I'm more positive than not on quantum computing being a reality, but everybody has to think about it in terms of it's like a GPU or it's like an FPGA. You run it alongside a CPU. So that's why people are calling it QPU now. So it's CPU plus QPU, not QPU on its own, which I think a lot of people have historically thought about it in that way. So they'll be in the data center. There's like 1 or 2 companies working on room temperature qubits to put on a PCIe card. That would, PCIe card like this. But that would be really exciting if it worked. But that's a longer term prospect of looking at that. When it comes to neuromorphic, I in general just have a problem with the fact that people call stuff neuromorphic just because it's brain inspired, but has nothing to do with analog computing. For me, neuromorphic is about analog computing, primarily about spiking neural networks. We have digital spiking processors from Intel, and a couple of others. So neuromorphic and other, non-von Neumann techniques, aside from quantum, things like optical, they're still a lot further out. They're still fundamental research. That being said, there are companies making money on that today. There are companies that have multi-million-dollar deals to supply chips. There they're developing the use cases. Some of them are relying on like traditional machine learning and then having to go through a converter to convert it into a spiking neural network and then learn how to read the results. It's just so many things going on with Neuromorphic, but Neuromorphic seems very much more of an edge technology for lower precision, but also super low power compute. I can't think of it being scaled up for big compute, like big GPUs and such. Whereas quantum, that is very much more a big compute solution. The funny thing is, I learned the other day, and I'll turn the interviewee relationship around. How much power do you think a 100-qubit quantum computer consumes, including the dilution refrigerator, including the traditional compute needed to power it and sort it out? How much power do you think?
I don't know. I know one thing. The people who are working on these things, they live in our neighborhood, and they say it's like it heats up like crazy, and you need all kinds of devices to cool it. So I don't know the
So
numbers, but I know that it's these are the real hot chips, right?
it's so a 100-qubit quantum computer plus all the infrastructure needed to support it is 25 kilowatts.
Wow.
A rack of AI supercomputing hardware is about 50 kilowatts. So if you think about it in terms of power consumption, there is expectation of quantum computing. It's 10 times more power hungry than traditional compute. Actually, no, it's less power hungry than traditional compute. The question
Especially
is,
when you use it in the hybrid mode. You don't have to have quantum for everything. You can use it for what is needed and then combine that. I think
that's
the
why it's
days of
CPU plus
hybrid,
QPU. Yeah.
yeah. I mean, it's the same thing with chiplets, right? You're not going to just use CPUs and GPUs. And for all you know, there'll be hybrid architectures, including possibly different architectures that haven't been conceived yet. And the whole history of technology is been like that. You start off with NMOS and PMOS and CMOS and all kinds of things that are hard to conceive today. But that's what makes this whole thing exciting. And then there are people like you and me who decided, after all, maybe we'll tell the story rather than actually do the programming. So there's a huge, huge need for it. I've never seen the demand for chip engineers or software engineers higher than what we have today. Do you think there'll be a day when robots will make the next generation of computers?
Oh, they already are. They already
Yeah,
are.
well,
It,
to the
it, it,
extent
it,
that design automation tools have been around forever,
well,
but they're not enough.
So the funny thing, the fun question to ask to people who are in this industry, to how deep they know about machine learning, is how many engineers does it take to build a chip? A modern chip on like say a Global Foundries 12 nanometer process. So it's still fairly advanced process. And traditionally the answer would be, like 1,000 or 1,200 if we're talking end to end. It turns out you can do it with about 20 today.
Very
with the right machine learning tools.
That's true. In fact, Pentium had more than a couple thousand engineers in those days. And today you can make almost 1 trillion transistor chip using a few dozen engineers, including the front end, back end, everything. It would not be possible. Most of my career was in electronic design automation. So yeah, it's going from traditional algorithms to now machine learning algorithms. It's just going to get more and more sophisticated. But I don't think it'll be like a push button robot creating the next generation. I don't see that happening in my lifetime yet. So
it's the, at what point can we make some of these machine learning tools make tools? And I don't mean things like Copilot or code design. I mean like, can you get a machine learning algorithm to create an IDE, create a design environment that can itself create its own design environment that's more efficient to itself? Before transformers were a thing, we had this, these online AI bots. You must remember the story. They created their own language to talk to each other more efficiently. That's the next step. Because right now with chip design especially, what they do is as the algorithm iterates through lots of designs, it keeps all of that data. So an engineer can go back and say, well, at epoch 3, step 15, it tried this, and this is the result out. So that in a way, engineers can try and see what the algorithm is trying to think about, trying to infer from that some of that data. The point in which those algorithms design their own tools to work more efficiently, that is the point where I think humans may lose the ability to interpret that data.
Yeah,
there is some argument that, like from the likes of somebody like Jim Keller, who's at Tens Torrents Day, he says that doesn't matter.
So essentially, it's going from iterative to recursive. So right now we are still iterating, and can you recur and create chip to chip to chip? Who knows? But it's going to be exciting. You know, Ian, we could be talking all day. Yeah,
that could be linear to exponential growth as well, right?
Yes,
that sort of thing as well. So we'll see.
And we've seen miracles happen in the industry. Nobody could have imagined when the first i486 chip or i864 chip, the RISC processor came about, that we're having these mega RISC processors and mega computers. Nobody could have imagined that in those days. So in fact, it's much more than more the way things are going. Well, Ian, we could be talking all day, and we're getting close to Christmas time and holidays for people, but such a joy talking to you. I knew you are much more than just a journalist and an analyst. So I could see the scientists hiding behind all this journalism and the tech potatoes. So please keep up the good work. I'm trying to be as technical as I can because it's hard these days to keep up with all this technology. I'm amazed how deeply technical you are and how much you've kept up with the times. And that's just exciting. This is really exciting.
It's thank you for having me on. I mean, the one thing I can say is my downtime, the time where I'm not earning money, that's the time where I relax. But I relax by going to IEEE events, right, where I can go be that information sponge. That's what gets me up in the morning.
But you can geek out.
Yeah, it's I don't always produce as much content as I would like to, and I sometimes look back internally and wish I wish I could have written something about that to explain it. But the fact that I learned about it is the key thing. Maybe I need to expand my team. That's how it goes.
Well, it's not always easy to scale when you're doing original writing. Maybe I do use generative AI to summarize things, but I don't yet trust it to create new content easily.
Yeah, no, I hear you. And yeah, whether it'll get there or not, we'll see. Fast-paced and always.
And to all the listeners out there, this is why this is exciting. I feel like when I'm conversing with people like Ian, I'm doing meta research. I'm no longer working on a chip or a system or a piece of software, but trying to understand what's going on. I don't think any one of us can predict the future 100%, but at least we can make judgment by learning from people, by looking at the world from a kaleidoscope. So kaleidoscopic universe is what we are in. And every day it changes from the quantum soup to the neuromorphic soup. So again, thank you. Please come forward. I would love to hear your stories as well. Ian, you're doing some amazing work. Please continue it. And please geek out. And when you're here next time in the Silicon Valley, come and visit us. And we can also go all the way to the beaches. I try to toggle between the two just to keep my sanity sometimes.
Sounds good. Thanks, Shankar.
Happy holidays.
Yes. Merry Christmas.
Merry Christmas.